This is part 7 of the Module 4 lecture. In this section, we're going to talk about the addition rule. And the addition rule is used to find the probability of the union of events. The addition rule has multiplication rules has two versions. In the first version, the addition rule is for events that are not mutually exclusive. So in this case, we're talking about the union of two events, event A and event B. So the probability of the union of events A or B is used the probability of event A plus the probability of event B minus the probability of the joint occurrence of events A and B. And because they're not mutually exclusive, then you know that there are some elements that are common to A and B. That's why this term for the joint probability appears in this version of the addition rule. Now, if the events, in this case A and B, are mutually exclusive, then the joint probability of A and B is 0, because there are no elements in common to events A and B, and therefore the probability is 0. Therefore, the addition rule simplifies to the probability of A or B is just the probability of event A plus the probability of event B. So again, in here, to apply the addition rule, you need to know if you're dealing with mutually exclusive events or events that are not mutually exclusive. Excuse me. All right, let's look at the first example and where we use the addition rule. In this example, a blood bank catalogs the types of blood given by donors during the last 5 days. And you can see there are two classification variables, the Rh factor and the blood type. And under the blood type, we have 4 categories: type O, type A, type B, and type AB. And under the Rh factor, we have positive and negative. And here you have the different frequencies that were observed. So if a donor is selected at random, the question is, what is the probability that the donor has a type O or type A blood? And the second question is, what is the probability that the donor has type B or is Rh negative? So again, as I suggested in the previous section, highlight or underline the events that are of interest in this problem. So here we're interested in the events type O, type A, type B, and Rh negative. All right, so let's calculate these probabilities. And notice that we're saying type O or type A, so we're looking at the union of those two events, and type B or Rh negative, so we're looking at the union of these two events. So to calculate the probability, the very first thing that we need to determine is whether or not the two events that we're considering are mutually exclusive or not. So in here, you know that a donor cannot have simultaneously two types of blood. So either you have type O or you have type A. Therefore, the event type O and the event type A are mutually exclusive events. So, and you can see it here on this table. So the type O is this column and the type A is this column. There's nothing in common between these two, the frequencies associated with the type O or with the type A. So in this case, we're going to use the version of the addition rule for mutually exclusive events. So to calculate the probability of the type O or the type A, then we calculate the probability for the type O event and then the probability for the type A event. So the probability of the type O, we're going to use a relative frequency approach. So it'd be 184. There are 184 individuals, so the 409 individuals that donated blood that have type O, and there are 164 out of the 409 that have type A. So if you calculate, you add these numbers, then you get 348 out of 409, and if you carry out this division, then you find 0.4 0.8509. So now we need to interpret this result. So the probability that a donor selected at random has a type O or a type A blood is 0.8509 or 85.09%. All right, so this is the case where you find that the events are mutually exclusive, and you use the, let's call it the shorter version of the addition rule. All right, in the next question, they're asking us if the donor has the type B or it has the Rh negative. In this case, then a donor can have a particular Rh factor on any of the blood types. So then you know that these are not mutually exclusive events. In fact, if you look at the case where the Rh factor is negative, which is one of the events of interest, and you look at the type B, then you see that there are 8 individuals that have type B, and they have an Rh factor negative, or a negative Rh factor. So in this case, we know that the events are not mutually exclusive. So now we will use this form of the addition rule, where we will have the probability of an individual having type B or having an Rh negative is the probability of having the type B plus the probability of having the Rh negative minus the probability of having type B and the Rh negative, so the joint probability. All right, so probability of type B is right here, is 45 out of 409 individuals. The probability of having an Rh negative factor is 65 out of 409. Now, if you notice, when we calculated the probability for the type B, we used these 8 individuals. When we calculated the probability of the negative Rh factor, we used the same 8 individuals. So we're repeating or double counting the individuals with the negative Rh factor and blood type B. That's why we're subtracting that part. So that's the joint probability of the type B and not the Rh negative. So I think you can see that by using this number and using this number, we're double counting this intersection of the two events. That's why we subtract. So if you carry out this operation, then you have 108 divided by 409, and that's equal to 0.2494. So interpreting this quantity, the probability that a donor selected at random has type B or is Rh negative is 0.2494 or 24.94%. All right, in this example, we use both versions of the addition rule. Let's look at another example. In this case, a machine fills plastic bags with mixed vegetables. So most bags contain the correct weight, but because the variation in the size of the individual vegetables, some packages end up being overfilled and some end up being underfilled. So a check of 4,000 packages filled in the previous month shows that 3,600 bags had the correct weight, 100 were underweight, and 300 were overweight. So here they want to know what is the probability that a package selected at random is either overweight or underweight. All right, so in this case, you can see that a package that is overweight cannot be underweight simultaneously. Therefore, the events overweight and underweight are mutually exclusive. So in this case, to find the probability that a package is overweight or underweight, then we'll use this version of the addition rule. And here I'm making the point that these two events are mutually exclusive, and they have there are no packages that could be underweight and overweight simultaneously. So that probability of that is 0. So that's why we use the shorter version of the addition rule. So the probability of a package being underweight or overweight is the probability of underweight plus the probability of overweight. So this is this underweight, there are 100 packages out of 4,000, and overweight, there are 300 packages out of 4,000 if you calculate those quantities, you find 0.025 and 0.025. If you add them, that's 0.1. So interpreting this result, that means that the probability that this machine produces packages with the incorrect weight is 0.1 or 10%. So this is an example with mutually exclusive events. Let's look at another example. In this case, the Florida Tourist Commission surveyed 200 people that visited the state during the year, and they found that 120 visitors went to Disney World, 100 went to Busch Gardens, and 60 visited both places. The question is, what is the probability that a tourist visited either Disney World or Busch Gardens? So in here, the events of interest is visited Disney World or visited Busch Gardens. All right, with those events, we can start talking about the problem. So in this case, the events tourists visited Disney World and tourists visited Busch Gardens are not mutually exclusive because some tourists visited both attractions. So again, these two events, visited Disney World and visited Busch Gardens, are not mutually exclusive. So if we define the events, as we said before, visited Disney World and then visited Busch Gardens, then the probability that a tourist visited Disney World or Busch Gardens, or the probability of A or B, is going to be the probability of A, which is tourist visited Disney World, plus the probability of B, the visitor visited Busch Gardens, minus the intersection where the two tourists visited both places. So if we only calculate these two probabilities, we're double counting those that went to both places. That's why we need to correct the calculation by subtracting those that visited both places. Again, if you carry out these calculations, you find 0.6, 0.5, and minus 0.3. If you do this calculation, then you find 0.8. So the probability that a tourist selected at random visited either Disney World or Busch Gardens is 0.8 or 80%. All right, so now we've seen three examples of the addition rule, which is another very useful rule when calculating probabilities. All right, at this point I will stop here, and in the next section we'll talk about the last topic, which is the counting rules.